Hello and welcome back to the alphabet of astronomy. Today it's brought to you by the letter I, and I is for inflation. Basically, inflation is an extremely short period in the very early universe, but it's hugely important. Now, inflation was first proposed in 1980 by a cosmologist named Alan Guth. The reason that he came up with the inflationary model was to explain away a few kind of lingering problems that existed with the Big Bang model. There were three main problems with the Big Bang theory that inflation was trying to address. The first was, why is the cosmic microwave background, or the CMB, so dang smooth? This is also called the horizon problem. Now basically, the cosmic microwave background is everywhere. Because we see it in every direction, we see it in places in the universe that should not have been in causal contact with one another. And yet, even so, the CMB is remarkably smooth. Its variations in temperature are on the scale of about 10 to the minus 5. Now, for comparison, a billiard ball, to be considered a proper billiard ball, must have a smoothness within 10 to the minus 3. So this is 2 orders of magnitude smoother than a billiard ball in every single direction, with things that were never talking to each other. So how could you create a billiard ball that smooth with a machine that couldn't know what the other part of the billiard ball looked like or had any information or contact with it? So this seems pretty surprising, right? You would expect that there would be some differences from these places that couldn't possibly know about the other places in the universe because they were too far apart. The second was, why is the universe so flat? This is also called the flatness problem. So one of the terms that cosmologists use to describe the universe is big omega, and this is basically the overall density of the universe, scaled. So a density of 1 would be flat, a density greater than 1 would be closed, and a density less than 1 would be open. And based on what we can measure today, so this is a quantity we call omega 0 because it's today, it's very close to 1. The universe is almost completely flat. Now this is interesting in and of itself, but for the value today to be so close to 1, because of the expansion of the universe, if there had been significant deviations from 1 in the early universe, expansion basically would have kind of exaggerated those differences. So for it to be very nearly 1 today, it had to be even more nearly 1 in the very early universe. So it had to be almost exactly flat. Now there's nothing wrong with having a flat universe. It's certainly a perfectly allowable outcome, but there's nothing like special about it. There's nothing that you would expect it to be 1 rather than greater or less than 1. I once had a professor in an astrophysics class in my undergrad that likened it to throwing a pencil up in the air and trying to guess where it would land, like how it would land. Sure, it's possible that the pencil could land on its tip and balance that way, but the chances of that happening are very low, even though it's a perfectly reasonable outcome. If that happened, you would probably think something was going on to make that happen. And the third problem was, why have we not detected any magnetic monopoles? This is also called the monopole problem. So basically, in electricity, you can have a single charge. Think of an electron. There's a single negative charge that has electric field lines from it. However, all of the magnets that we have ever detected anywhere in the entire universe are dipoles. Think of how a magnet has a north and a south pole, and the magnetic field lines go from one pole to another. They don't radiate outwards from a single monopole. But based on our understanding of the very early universe, we actually think it was totally possible that these magnetic monopoles would have formed when all the different forces were kind of freezing out, which that'll be a topic for another video. But suffice to say, theoretically, we expected there to be magnetic monopoles, but there are not any that we have ever found. There was a couple that were like, oh, maybe, and they never panned out. Okay, so cosmologists were kind of puzzling about these 3 things about the universe. Of course, like I kind of hinted at with the flatness problem, you don't have to have a solution to these necessarily. You could just say, well, this is the way the universe is, and it just happened to come out this way. And that's certainly possible, but it's not very satisfactory to scientists, because when you have these kind of very strangely perfect values, like an almost perfectly flat universe, the natural question is to ask, what is causing this? Why? That's science. Why, right? So rather than invoking just random chance, Alan Guth and other cosmologists developed the inflationary model. So how does inflation solve these problems? Okay, so first let me tell you, when I said extremely brief and extremely early universe, I really mean that. Like in ways that it is pretty much impossible for the human mind to comprehend. So we're talking about when the universe was 10 to the minus 36 seconds old. Now keep in mind, 10 to the minus 9 is a nanosecond. It's it's incomprehensibly short of the period of time that we're talking about. And inflation lasted about 10 to the minus 34 seconds. So from about 10 to the minus 36 to about 10 to the minus 34 seconds, you had this period called inflation. But no matter that it was that short, it was hugely important for the universe that we see today. The idea of inflation is that at the beginning of this inflationary period, the universe was actually much, much more compact, and during inflation, it underwent an exponential expansion. Now, the universe is expanding today, but that's not what inflation is saying. Inflation is saying that the universe expanded exponentially. So during this flash of time, the universe increased hugely in size. And what this meant was that the compact universe, where all of the points were in causal contact and in thermodynamic equilibrium, basically got ballooned out and kind of pushed away from one another. And so this kind of goes back to the horizon problem, right? So it answers, why is the CMB so smooth? Because back in the day, the CMB was in thermodynamic equilibrium, all of the points of it that we can see, and it was only that this rapid period of expansion kind of moved all of them apart, but they didn't lose that information that they had gained from being in thermodynamic equilibrium with each other. And this sort of very rapid expansion also kind of smoothed out and flattened the universe. I mean, this is not exactly what happened, but just, think about blowing up a balloon. Any section on that balloon kind of becomes less curved as it gets blown up, and it gets smoother, right? So it's becoming smoother and flatter via inflation, which solves both the horizon problem and the flatness problem. So what about magnetic monopoles? Well, actually, inflation also helps with that, because basically in the time before inflation, there was not enough time for very many magnetic monopoles to form. Remember, this was 10 to the minus 36 seconds into the creation of the universe. So the magnetic monopoles that did form got pushed very far apart during inflation. And so this means that in the present day, the density of magnetic monopoles is extremely low, and this means it's perfectly plausible that we've never detected one, because there's just not very many of them in the whole entire universe, because there was only a couple that could have been created before inflation, and after inflation, the conditions weren't right anymore to create magnetic monopoles. So it's a pretty handy model, and it's pretty cool. And so this will see, you'll see a lot if you see this kind of diagram of the universe, the history of the universe. This section here where it goes from just kind of being the point. Now this is after the Big Bang. So this part here where it goes, people kind of, I think this is the Big Bang because it looks like a bang or an explosion, which is not what the Big Bang was anyway, but we're talking about inflation here. So no, this is actually after the Big Bang. So the Big Bang was the start, and then again, 10 to the minus 36 seconds later, lasting for only a brief fraction of a second, the universe went huge. And then it did kind of continue to expand a little bit from there, but nothing like inflation. Now, obviously, I'm skimming over most of the details of the inflationary model. The actual details have changed quite a bit since it was first proposed back in 1980. It used to be the false vacuum theory. Now it's called the slow roll mechanism, where basically there's this potential that the universe was going down that led to this exponential expansion. But I'm not going to worry about the details. You're not trying to become a cosmologist. I just want you to know what inflation is and why we have this model and why we think it is a good model for explaining the universe that we see. So even though all the details of the model have changed, the basic idea has remained that the universe in its very early stages underwent this extremely exponential, rapid expansion that kind of created the universe that we see today. Now, this is pretty widely accepted among cosmologists, but I will say that there are some detractors. It does have its critics and people that think that it is not a good model, so that's science for you, and this is definitely, the details of this model are definitely still being worked on actively by cosmologists. The observations that we have been able to make have basically kind of been in line with what we expect from inflation. For example, back in 1980, we thought the CMB was smooth, and the more we measure the CMB, the more smooth we realize it is. One thing that scientists are also trying to do is measure something called B modes within the CMB, which could give us hints about things before the CMB and could help maybe give us some ways to test different inflationary models. And like I said, this is very actively being worked on by cosmologists, so there's still a lot of open questions about the details relating to inflation. But the general idea of this exponential expansion in the very early universe that solved these three main problems of the flatness problem, the horizon problem, And the monopole problem is kind of what I want you to take away from this video. If you're interested in reading more about some of the critics of inflationary model, I will link a rather famous Scientific American article down below that was from I think 2017, where there was a couple vocal critics of the inflationary model. So there you have it. That's inflation, the exponential expansion in the very early universe that helped explain certain conundrums arising from the Big Bang Theory. So, hope you learned a little bit of something, and I will hope you will join us for the letter J. J is next, yes. J. Thanks so much for watching. Have a good one. Bye.